All right, welcome to the next session of Deep Dives live on Saturday afternoon, kind of depending on where you are, at least in Europe. My name is Johannes Mikko. I'm one of the founders of Deep Dives, full-time instructor for all of the cloud hyperscalers, and have quite an extensive background in software development, cloud architecting, machine learning, just name it, right? And together with me, I have my old friend Mikko, whom I've either been working with or working against, I guess, for the past
both
20 plus years, soon 30, right?
About
Anything
30
you
years.
want to add, Mikko?
Just keep on doing that. Just whatever you want to say. We have similar background. Software development, software architecture. We both started before this became our profession. We started with computers in the late 80s, maybe. Or so.
Yeah, our common background isn't from Finland, but nowadays we live like, I think, 2,000 kilometers apart. I'm in Portugal and Mikko is still back in Finland. So just kind of as a comparison, it is currently 20 degrees outside here in South Portugal. And you, Mikko?
It's snowing outside.
Yeah.
Probably minus 10 or something. I haven't looked out yet.
You haven't dared.
Actually, it's been snowing so much that they are in trouble at the airport, which is not normal. So there's
All right,
a lot of snow.
So I chose a title for our session this time. The title is called Frugality in Modern Service Development. And I put a typo in there as well. It's supposed to be development, not development. So just fix that. The idea here is that I'm, of course, referring to Dr. Werner Vogels' keynote at reInvent, where he published or made public a new website of his about frugality as an architect. And I didn't like to copy the title, Frugality as an Architect, because we're maybe a little bit more software development oriented. But then I appreciate that frugality is not only, software development dependent. It's also about architecture. So I decided to use the term service development instead, because that's basically what we did, right? We write software that run some kinds of services. Just a little bit of background from my point of view. I really enjoyed the keynote. If you haven't seen it, there should be a link to the YouTube video available for you. It's really nice. It talks about a lot of things that I have been talking about when giving DevOps lectures, sometimes even software development lectures or instruction. And Mikko actually gave me the idea of how to contextualize this through history. So you want to talk about that for a couple of minutes and how you see that this is the same thing that happened back in the 60s, 70s?
I'm just wondering, what have I said to you?
You told us about time sharing, right?
Mainframes, or
Yeah.
you mean that back in the day when resources were not limitless in the mainframe time? I'm not that old that I've been working extensively with mainframes. Or am I? But I've heard from my colleagues, and I've learned from my colleagues that back in the day it was really important to design your software and your databases, basically most of the time relational databases, if we talk about data stores, very carefully and really pay attention. How do you access your database and what kind of queries you have? And then when we moved to, let's say, regular on-prem servers, you had a really big box, a really big server, and you were able to write really bad code and nobody complained.
Yeah, I guess
And
like
and we kind of forgot how things were done, or maybe we never even knew how things were done in the mainframe time. But that's one of the problems, and that's why we probably have the Frugal Architect 7 laws there now, to kind of get the control back and really pay attention
it's
to
like
how you do things.
yeah, it's like back in the 60s and 70s when like especially in academia, when people were kind of writing software and then running it on the main the mini computer of the of the university, your department would get charged based on the amount of seconds that you would be using the CPU. So to keep your boss happy, your code would better be well optimized, right?
It
So
made sense to write good code, at least
yeah,
from
there was a clear kind of
efficiency point of view.
financial thing.
Yeah.
As soon as your code would be unoptimized, you would get hit by a big bill, right? And this was, of course, always retroactive as well, right? So you kind of didn't know beforehand how long your program is going to run for. You could, of course, do some simulations, but you wouldn't really know. So that all kind of went away with microcomputers, both on a personal level. So the software that would be running in the microcomputer would most of the time, especially like back in the 80s, have full control over the whole microcomputer, whatever resources would
Those
be
were the
available.
days.
Yeah. So we just use that. And then if we're doing something simple, then it doesn't really matter whether or not we are doing that in an optimized way. The only reason why you would try to optimize something is if you would do something that would be complex, that would otherwise take too long for the end user to wait for. So we kind of brought that culture with us towards service development, or server software development. Because back in the old days, there wouldn't be any virtual machines. We would literally run our software, our product, on a physical box. And then as long as you didn't hit the limit, either CPU or memory, of that one box, nobody would care about the performance of your software, right? So there was the kind of idea of true idea about premature optimization back then, right? So it was more important to get throughput or velocity to kind of get an idea into production, no matter regarding the implementation performance per se. And then kind of once we get to the or at least close to running out of CPU or memory, then we would revisit the code and try to optimize it in some way, right? So it's kind of a technical debt for velocity, and then repaying it once you get there. And that all makes sense. It really did.
And just to remind everybody, when you started with a new service, you actually could just order a new server altogether. So you always had a bare metal server just for this new thing that you were building.
Exactly. Yeah.
And first of all, that was really slow. Like, it takes time to get that server, but you had, from your service point of view, you had almost limitless resources, as long as your algorithms were not completely awful.
Yeah. And then something happened. Well, virtual machines happened, containerization happened, co-location of services on the same hardware happened. And now with serverless compute, Lambda, etc., we're back in square one, where we are paying per millisecond of CPU usage, basically.
Except we have very good visibility to the cost. We
Yeah,
can
exactly.
immediately see how much things cost. And that's probably different from the old times.
Exactly, and that was kind of what warmed my heart when I was listening to the keynote of Dr. Vogels. That he kind of went back to this idea of making sure that you know how much maybe CPU you're using, and just to make a note here, we're not throwing away the idea of gaining velocity versus performance, right? We can still do that. It's totally okay. We can choose to do something non-optimized just to get velocity, so to get the feature out there. But now we have the choice of actually seeing what the cost implication of that is, and then maybe considering whether we want to rewrite a functionality in a more optimized way, if there is
Or
a
just
business case.
re-architect, choose different components.
Yes, exactly.
And that's
Like I said,
something that you couldn't do in the past. I just
yeah,
fondly remember the past where when you started writing something, you had some sort of a software architecture there, and you were just doing things the same way you were always doing it, and it was really difficult to change it. You were stuck
absolutely.
with the approaches and the solutions that you were comfortable with. You knew that these would work, and but also from that time, the optimization, if you do it, just postpone it. You are building huge technical debt.
Yeah,
And I think that there always has been a middle ground there, that if you know that this is an awful way of writing code, then why would you just ignore that and maybe do it properly in the beginning already? And the more experience you have, then it's easier to write things properly from day one without sacrificing the speed or agility, in my opinion. But then, of course, people do things differently.
yeah. It's a little bit more complicated. And I like the idea that you should still try to kind of at least semi-optimize or locally optimize from the beginning. But now with the current technology that we have available, we need to revisit those choices to check whether whatever we were thinking back then is still valid now.
Yeah, for
Or whether
example,
we should
just
actually,
maybe it's better to choose a different database.
yeah,
And back in the day, it was, and not that long time ago, it was really difficult to choose a different database afterwards,
yeah,
especially if the organization only had one type of database. Then, well, you wouldn't change that because you had
yeah,
no
exactly.
control on that.
Yeah. So okay, and just we are talking a lot about software development and code and programming, but in Werner Vogel's view, this is actually true also for kind of generic service architecture itself. And maybe we should just use a little bit of time to talk about Werner himself. So I've got the Wikipedia page here. I'm just going to post that into the channel as well.
Could you zoom in a little bit?
So yeah, oops, this one.
Yeah, thank you.
So he's Dutch, which you can still hear from his accent. He's got a really nice Dutch accent. And it's interesting that he actually didn't start out as a computer scientist. Instead of that, he was actually a radiologist. So studying how to take X-rays and how to interpret those X-rays. And actually, during his work life, researching cancer treatments, his kind of mentor or boss told him to take up a career in computer science. So he started studying computer science fairly late on, and he actually went to an University of Applied Sciences, so not even a research university. But then he got himself out of there, and then wrote a PhD on distributed systems, and then got into the US, into Cornwall as a researcher, researching distributed computing. So that's kind of the background. And then he had some startups, and I think it was in 2004. He joined Amazon, and then fairly quickly became CTO, vice president for technology as well. And so he's a fairly smart person. But just for any viewers that are maybe in their early 30s, that's when he went to computer science, right? So he did, that was not his first choice. So it's totally okay to make these kinds of career choices later on and then still become somebody that actually
That's actually quite impressive.
It is a smart person.
Make a shift like that.
Yeah. So the website he published during reInvent is this called thefrugalarchitect.com. So he has a different website called All Things Distributed that he uses for his blog, but this is kind of a specific website for this frugality point of view, right? And in that he just kind of digests basically the gist of what we have been talking about here for the past 15 minutes into 7 laws. And I don't want to go through these one by one. I just want to, everybody can go read those. They're fairly short laws, so fairly interesting to see. But in my opinion, this kind of goes down to a couple of key issues. So the first key issue is observability, and this is in law number 4, I would guess. You need to have visibility on your software development lifecycle. So first of all, of course, we all know that you need to have visibility onto your service architecture, kind of how things work. Are they available? How much do they cost? That kind of stuff.
And before you continue, 5 of the 7 laws mention cost, and that should tell something as well.
Yeah, well, frugality itself, being Dutch, right? I can say that. But yeah, so observability is about not only about knowing what the state of your system is right now, but also be able to make educated guesses or estimations about what your system is going to be like in the future. So we have kind of a time series of visibility metrics, and this is not only about the production environment that your system is running in, but also your CI/CD pipeline. Like in your CI/CD pipeline, you're running some tests. Well, how do the test run times change over time? Why does a single unit test for a single module suddenly take longer than previously? Can you explain that? Maybe there is added functionality there. You can. Maybe somebody decided to import half of the internet, and then it's not very good, right? So kind of observing not only the environment where your service is running, but also observing the whole pipeline. How many lines of code are there? Why is there suddenly double the amount of code in a single module? There might be a good reason for that, but it's something that you should, every now and then take a look at and try to explain. And then if there's something unexplained, then that might be something to take a look at.
From software architecture point of view and software developer point of view, the observability is super important. And when I'm looking at it, I'm not thinking about the cost. I'm looking at how can I know what is happening in my system just from the software development point of view. If there's a bug and you need to fix it, can you really tell what are all the components that are working together? The documentation usually doesn't cover that. The documentation is old, it's not up to date, maybe it was never written, or it was written but the implementation doesn't match what the documentation says. And if you're a new person to a specific project, you have no idea what are the components unless you have good observability and good visibility to everything. And back in the day, all you had was a bunch of logs. And from the logs, you had to figure out what are the different components that are running in a distributed system.
Exactly.
And
yeah,
that was hard.
All right.
And that was just, and that's me talking as a software developer. And I was not thinking about the cost here with observability, but yes, definitely. You need to have observability to the cost as well.
Yeah, so observability, if we simplify the architecture a little bit, let's say that we're talking about serverless architecture with, Lambda functions as the compute implementation. Then basically observability tells you, how many times has your Lambda function been called during the past month and what the average runtime was. That gives you your Lambda bill, right?
And the relationship between different Lambda functions.
Oh, yeah, also that. So that kind of allows you to take a look at, okay, so where is my cost? What is my cost actually composed of? Now, purely on the compute side, let's forget about storage and networking. They work similarly in their own domain, but just purely from the compute side. So you can actually take a look at what your cost leader is. And then you can start to make a kind of a business proposal. Well, what would it mean if we could, let's say that our Lambda function takes 400 milliseconds to run for whatever reason right now. What would the cost implication be if we could shave that to 300 milliseconds instead of 400 milliseconds? And based on the observability data that you have, you immediately know, well, then you're going to save this and that many dollars per month from that onwards. So then that could give you a budget, right? So does it make sense to try to rewrite this function?
I haven't, now that you mentioned that, then when you have good observability, you might not have realized that actually the reason why you have this one Lambda function that takes, let's say, 400 milliseconds, maybe it's because the Lambda function is calling other Lambda functions and it's just waiting for the other Lambda functions.
No
and then you re-architect and not just make it more efficient, but then you have the idea that, hey,
and
this was implemented incorrectly completely. You need to do something else like step functions or something.
You can't have Lambda functions calling Lambda functions. That's not allowed.
But if you have a chain, yeah. If the Lambda function is there at the beginning and it is waiting for other resources, then is it the correct way to implement?
Yeah, we don't do that over here, right? No cursing allowed.
If you look at other people's implementations, then you might find things like that.
So like, tip number one, whenever your Lambda function is waiting for something, don't use make step functions to do that, right? So that's how we work. But yeah, so Lambda functions with observability can give you an idea of how to identify the places where you should do optimizations. Because if you have a Lambda function that runs once per month, and it takes 2 seconds to run, an unbelievably long time.
It can take 15 minutes to run.
No, we don't go there.
But it's once per month, then maybe it's okay.
That's on the border, right? So
yeah.
But we so if it's just once a month, then maybe we choose velocity over performance, right? Because it doesn't make sense to re-engineer that to make it more efficient, as it doesn't really affect any of our requirements. And that's kind of where we go to with law number one here, right? So cost needs to be a requirement. Similarly to latency, very often we're seeing that we have this kind of latency budget that we know that our end customers are sensitive to latency. So whatever action they're doing on the user interface basically gives us some limited amount of milliseconds to spend from the user interface all the way to the back end and back again. And then, of course, in modern architectures, we need to divide that budget between multiple services even. So instead of just thinking about that latency as a requirement, we can then also think of cost optimization as a requirement. Not maybe a specific budgeted requirement per se, but as pressure, pressing development to a certain direction, which is
latency as a requirement has been around since day one.
Yeah, of course.
I've seen that as from, if you're looking at the specification, it's always mentioned there. It's easy to say, yeah, we need to have this and that. So that is nothing new. Like to have latency, but to have that cost there as well. Then
because it kind of starts to be similar things.
And if you have larger latencies, it means that you're doing something for a longer time, and that actually costs. Usually, that costs.
Yeah.
Somewhat.
So just to pull in architecture for a short while. So because we're talking about latency here. So one way to also decrease cost and/or latency is to change the architecture.
Like from synchronous to asynchronous implementation.
No, even more simple, just adding a caching layer.
Yeah.
So especially when we're talking about fairly large relational databases, whenever you're running out of capacity on your database, the step up to the next size of database can have a huge financial impact. Basically, is either doubling your database costs or at least adding 50%, because that's what the steps are, right? There is no fine-grained possibilities there. So, like if we're talking about large instances, this could mean like $1,000 or $2,000 more in your database costs alone. And the problem here is that you're just pushing towards 95% usage of your resources, which for me is actually a great place to be. Yes, I'm getting what I'm paying for, 95% usage. But the problem, of course, is that whenever there is a peak, then we get decreased user experiences via added latency because queries need to queue and that kind of stuff. So what we want to do is we want to raise the make a larger instance. And of course, the problem is that if we have 95% usage of our current infrastructure and we're doubling the size of an instance, then what is our usage like?
About 50.
Yeah, 47.5. That sounds awfully low to me. I'm like,
I was like my age.
Yeah, I'm like paying so much, but I only get 47.5%. So kind of one of the ways to smoothen out this is to actually add a cache cluster to it. So the cache will take care of some of the repeated reads from the database. So it'll take off some of the requirements from the database, and it might very well be cheaper than getting
and the cache can be in different places.
Yeah. The same is true, of course, also for Lambda invocations. Like if your Lambda does the same thing all the time with predictable outcome from a particular input, then maybe it's cheaper to serve that via cache than by actually calculating that every single time. So there are also these architectural ways for Frugality, for kind of getting more out of your architecture for a cheaper price.
And at that point, you have already, of course, figured out if you have bad queries to your database. And you have optimized the queries, and there are lots of places and lots of things that you should do anyway, and not.
And that's maybe more debugging than actually, anything else, in my opinion. But
I would say it's also about writing. As a professional, you are writing better code when you have more experience, you know beforehand that, okay, that query will be a problem. You have 11 joins in that one query, then that will be a problem sooner or later. And I would say you have to do all of them. Like think about, for example, caching, but also you have to look at critically at your like software architecture. That is this correct? It's not only about optimizing
Code.
like the cache, or the latencies do come from so many different places that you have to look at from different directions. That
absolutely. All right. So with regards to code, there has been some research, which surprisingly enough comes from Portugal. This is from INESC, which is a national kind of information or technical institute, research institute. And as it happens, Werner Vogels was actually working at INESC at his very early career as a computer scientist. So interesting to see things coming back together again. Again, I'm going to share the paper URL. And in this paper, they are measuring programming languages using different kinds of benchmarks. And what they are actually measuring is the amount of energy being used for a specific, so in joules for a specific benchmark, then the time, the CPU time that was used, and the amount of memory that was used across the different benchmarks. And I'm just going to, I have the paper in the video here, so I'm just going to scroll down to kind of see what the end results were. And
the most energy efficient one is C.
C, right? And that's kind of the benchmark against where we're looking at all of the other ones. So from an energy and time point of view, energy and time go pretty much hand in hand here. So the best one is C, which kind of makes sense if you've done any software development. And then the second one is actually Rust before C++, which is slightly surprising. But this might be due to library usage. And then next up, we've got Ada, which is a fairly old language, then followed by Java. So
Java is the number for Java from energy point of view is 2, so it's uses twice as much energy compared to C.
As C, yes. Whereas the Rust number is 1.03, so it uses
basically the same
3% more. Yeah. So at the very end of this list of programming languages, we've got Python, which takes roughly 76 times the amount of energy than compared to C, and Perl, which takes roughly 80 times. And
how do you translate? Can you translate this directly to the execution time as well?
That's on the time side, right? So the next column is about time. That's CPU time. And these, of course, are different because different actions on the CPU take different amount of energy, right?
And I'm asking because from end user point of view, if Python uses 76 times more energy, does it matter from the end user point of view, or is it?
Well, it shows up on your energy bill, right? Especially if you have.
What does it mean from the end user's point of view?
If you have a laptop, then it shows up on your electricity bill.
If you're using AWS services,
no, there's no.
Exactly.
From AWS services point of view, there's no. And then you look at the time and the memory parts.
So in that sense, from the end user's point of view, well, of course, we should think about the environment, but maybe the time
so
is more
Python
important.
would be 72 times more time consuming.
Almost hand in hand with the energy as well.
Yeah, there are some differences which have to do probably with the compilers. So whether they are doing some kind of interpretation or just-in-time compilation into machine code. So that kind of probably decides the difference between time and energy here, because if you're doing interpretation, you need to run two programs, the interpreter and the actual end program.
And if you think about this, then one would just, okay, let's do everything in C because it's more efficient. And you're doing things wrong then.
Yeah.
From my point of view, my background is with Java, more than 25 years of Java, and C, which I learned before I learned Java, is way too dangerous a language to be given to almost anybody. It's you run into trouble. You're going to make a huge mess if you just use C. And bear with me, for most programmers, software developers, it's much better to use a language that's safe and you're not leaking memory or have problems like that. And if you go down to the list to Python, which is very inefficient in that sense that it uses a lot of energy and time, but the time to write the code and to maintain it might just dwarf that number. It could be so much easier to maintain the code that it's okay to use Python.
Yeah, that's kind of why Rust. That's also kind of why Rust is so interesting here, because Rust is type safe, and even though it doesn't have a garbage collector, it has built-in memory management capabilities. So Rust is kind of a safer language with almost the same time coefficient than C. So that kind of starts to hit some kind of a sweet spot from that point of view. Also, Go is fairly up on this chart. It also has a good kind of lines of code versus functionality ratio, which actually Java doesn't often have. Well,
it's very verbose. but if you think about the total cost, then it's definitely not only about how efficient the program itself is. It's also about how easy it is to write the program, how easy it is for someone else to come and continue the project or maintain it after 10 years.
Exactly.
So it's actually fairly complex. So if we stare at these numbers only,
these are just
that's not the whole truth, in my opinion.
Yeah. So this allows
this is really interesting data.
Yeah, it allows us to choose between performance and then velocity, which could be kind of this combination of readability of code and the productivity of the developer.
And if you have a very limited system, for example, some integrated system, then efficiency is, you just want to use as efficient approach as possible, but that's definitely not always the case. For example, if business logic is more important than the actual efficiency, you're running one complex method that is very difficult to implement from that, like it's just complicated, then maybe use a language that's easy to write with, instead of, if you have a busy loop that's run millions of times per second, then maybe you want to have the most
and this is maybe a little bit unfair towards Python, because I haven't actually read what it is using, because we're doing kind of some stuff that is somewhat interesting in Python. So because if they would be using, for example, NumPy, the NumPy library, which uses vectorized mathematics, which is written in Fortran, right? So it's actually not written in Python. The library is written in or probably already pre-compiled into machine code itself. Then when we're doing something data intensive like machine learning, the Python part is actually just the very high level how to run things, and then all of the actual compute does happen in languages that are different.
That's a good combination. Something that you can fairly easily write, and then the actual busy loop is implemented in different language.
Yeah. One interesting thing here on the very right-hand side of this table is the memory consumption. And here Pascal is leading. And this is
why is that?
It is due to the data structures used in Pascal compared to others, right? So
that was actually one of the first languages that I've learned.
Yeah,
and forgotten already.
After basic.
Yeah, after basic Pascal.
Yeah. But yeah, so here we can see that Fortran and C and C++ and Go are fairly high up. This is because we're doing a lot of data structures natively in these languages. And then here Java starts to be very bad.
Uses 6 times more memory than Pascal.
Yeah, maybe due to garbage collection, lazy garbage collection, and then also the 64-bit pointers, and then using object reference, of course, adds to all of that. But also kind of interesting, but the differences here are way smaller than on the time side. And then if we kind of go back to AWS and we think how Lambda scales, you get more memory as you get more CPUs. So based on this chart, I would say that, when comparing different languages, then memory is not going to be the pressure point, rather time is going to be the pressure point. So it's probably better to look at that and then just to maybe cross-reference with memory, so that if you're moving from C to Python for whatever reason, then you're going to use, roughly 2 times more memory, but you're going to be 72 times slower. Well, maybe the other way. If you're moving from Python to C, you're going to be 72 times faster, but then your memory consumption is only going to half.
72 times more dangerous language also.
Yes, at least.
So that it's not so easy just to choose C always, because
no, but this is
different kinds of headaches after that.
Yeah, this is what I like.
Certain projects, that's completely the correct choice, but definitely not for every project.
Yeah, I like the Rust being so high up in here. And that's kind of one of the reasons why Amazon has decided to rewrite quite a lot of their backend stuff in Rust. So all of their networking stack is written in Rust. This is due to the Rust code being able to prove that an algorithm is correct if it is run in Rust. So like mathematically proof. This is very important for security. So that's why the networking code is written in Rust in AWS. And recently they've also changed the S3 backend, the storage backend code into Rust from Java.
From Java, okay.
Yeah, quite a lot of the front end stuff is written in Java still in AWS. So it's interesting to see, and this has also made me. I've been doing stuff in Python and JavaScript, like Python for kind of admin stuff, like a script that moves things around. It's easy to write, and performance doesn't really matter. So just use that. And then JavaScript for like backend functionalities, because of the amount of lines of code compared to functionality. It's really, I have this rule that, a single function cannot take more than one screen full of code. So you can immediately see what is going on. No need to go anywhere else. But I've kind of thought that I should convert over to Rust for those hotspot parts of the code, the ones that get really called often.
I have a question for you.
Go ahead.
Imagine you have a Lambda function, and let's say it's written in Java because I've wrote it and I'm most well, I'm a Java guy, or at least I used to be.
Your
Then
Java is better than your English.
much better. And then if I switch from using Java, let's say it's just business logic, something that runs in, I don't know, 50 milliseconds. So very fairly straightforward. If I convert that or rewrite that in Rust, how big are the overheads there? Because if you be in charge for 50 milliseconds, how much would you shave off that if you switch to Rust? I don't think it's going to be just divide the time by 2 or
No. Of course.
so there's some overhead there always.
Uh,
So it would be
well, this
actually
is just
interesting to see how big a
okay.
difference it would make.
So this is just the based on these benchmarks that we use.
Yeah, of course.
So for these, it's true.
But yes, if you're running just that, but if you're invoking Lambda functions, then it would be nice to see how that translates. So have a similar study where you are actually
So
running some
I can tell you a little bit what you would get from moving from Java to Rust. Okay. First of all, your cold starts are going to be a lot faster, right? Because with Java, the virtual machine has to start. It needs to create that graph of all of the whole class tree, all of that stuff. Gone, nothing like that. Second of all, your deliverable
and you're not paying for that, but that's actually part of the latency.
It's latency. It's part of your latency budget anyway, right? And then your deliverable or your artifact can be a lot smaller because it's just the machine readable code. So it's more secure also from that point of view, that you don't have this.
Why it's more secure if it's smaller?
No, but you don't have that dependency, that additional Java runtime environment that could have a bug in it.
Yeah.
It's just your executable
yes.
That's there. So it's smaller and there's more security because there's a smaller kind of a attack vector surface. So there are these additional things, and then most likely writing the same functionality in Rust takes you longer than in Java, especially you, because you don't know any Rust.
Yeah, definitely. In the beginning, it would take more time.
Yeah, but we can only take these numbers as a kind of a guideline. So this is something that we could kind of start off with and then say that, if we have a specific function and it's written in Java and it costs us currently $1,000 a month for invoking that Java function. Well, if we would rewrite it in Rust, we could possibly reduce that by 50%, right? So to $500 per month. So now, how long does it take us to rewrite it? Yeah.
And if you're doing some sort of microservice architecture or something similar, I don't mean that it doesn't have to be microservice, but then you can, and for example, if you're using lambdas, then you can actually easily just pick those lambdas that have the longest latencies or which are running, giving you the largest cost, and then just re-architect them and not the whole application, because I know from business logic point of view, it's utter nonsense just to rewrite your whole code base, because you are going to be stuck with testing and endless list of bugs if you're rewriting everything.
We call this like targeted optimization, right?
Yeah.
So just the ones that.
Just the ones. And this is something that you couldn't do in the past. On-prem, you were stuck with architecture choices that were made probably for you. So you couldn't you couldn't change the language. You couldn't change how different parts of the.
Well, we had JNI, remember?
Barely, but still, if you're part of an organization that has a specific way of writing code, you're stuck with that.
Yeah, exactly.
And that's happened with me. So that's actually one of the reasons I've been using Java for so long, is that, well, I've been working with clients who use Java and nothing else.
As will most of our audience in all of our instruction that we have ever given. Maybe except for
continuing it just a little bit with that, but from the software maintenance or your code maintenance point of view, it's very good that you have a limited set of languages and architectures. So if everybody's using a different front-end framework for every single project, it's impossible to maintain in the long run.
Exactly.
You have to find the balance there, but it's good that it's no longer that you're stuck with one specific programming language and one specific database. And that's a really good thing.
All right. So we've almost used up our allotted time. Any final remarks, Mikko, you wanted to share with us?
I don't know. We
Save
could
some
continue this
for
discussion
future.
for a very long time.
Yeah, we've
This
got
is
more to
really
come.
interesting, and also for someone who is like has been writing software for a long time, it's a really good thing to actually see this. For example, this kind of a chart that, okay, maybe Java is not the correct tool for every situation. And that takes time for those who start now and they are cloud native from day one. They are not limited by the decisions that were made a long time ago.
Exactly. Yeah. It's going to be interesting to see how this changes the world. We're kind of bystanders, right? So we of course try to instruct our audience to take these kind of things into account when they're doing their own architectures, their own decisions. But then on the other hand, we can just kind of sit by and look at what really happens in the world. And it's good that it's like, going back to Dr. Vogels here, it's good that it's now finally a proper talking point. Like I've heard for a very long time felt like I'm the only person who wants to talk about this. And now we actually get somebody with a platform to talk about this as well. So
it would be nice to see a study also from like software maintenance point of view, which languages are easier and which ones are difficult to maintain, because that's one part where the cost comes from.
I think ACM does a study like that. I can try to look for that for our next session. At least I have seen it was somewhere together with the popularity of programming languages. There was also some discussion about the kind of usability and long-term maintenance point of views.
And for organizations that are cloud native and start now something new, it's easy to make good choices there. But if you have already millions and millions of lines of code, how do you change that?
Yeah,
that's difficult.
Yeah, so
maybe you go back to the observability and have a good overview of where does the cost actually come from, and then well, pick up those places where it's easy to change something and like re-architecture or different database, or just optimize those parts of your code which are used a lot.
Yeah, maybe we revisit this discussion on a later date, right?
Sure.
Okay, so I think that's it for us this time. Thanks again for viewing or listening. My name is Johannes Mikko, and I'm joined here by Mikko Nieminen. We're both instructors for deepdives-eu, and hopefully see you either watching the stream next week Saturday at noon GMT, or maybe in a future training that we're instructing for you. Anyway, thanks for being here, and see you later. Till then.
Bye-bye.
Bye.